We are finally ready to talk about current, the flow of electric charges through our circuits. But first, we need a little science history background. According to Wikipedia, Benjamin Franklin called the charges positive and negative. He knew we had two types of charges. He called them positive and negative. And he knew that they got transferred from one object to another. And he even came up with the idea of a flow, like a fluid flowing from one object to the other. Unfortunately, he didn't know which charges moved. He guessed positive, and now we know that that is incorrect. So a lot of the work early on with circuits defined current as the direction positive charges flow through a circuit. We now know that positive charges don't move. It's the negatives that are moving in the opposite direction. But we're stuck with this convention. So when you see an arrow in a circuit indicating the direction of the current, that's this hypothetical movement of positive charges. The real movement is the electrons moving in the opposite direction. But how do we know positive charges are stationary? They stay with the nucleus of the atom, and it's the electrons, the negative charges, that can move through a circuit. There were two experiments that were done about the same time, and they both lead us to believe that it's the negative charges that are free to move in our typical metal conductors. The first one is very similar to what you may have done when you were a kid. If you had a wagon, at some point, you probably had a ball sitting in the back of your wagon. And if you pulled on that wagon and it got it to accelerate to the right, the ball would lag behind because the ball is made out of mass and it has some inertia, and it lags behind a little bit and ends up at the back of the wagon. The same thing happens with electrons. They are particles with mass. They have inertia. So if we take a piece of metal, a conductor, and there's some particles with mass and inertia in this metal that are free to move around like a ball sitting in the back of a wagon, and we accelerate our conductor, then whatever is free to move around will lag behind and end up built up at the back of the metal conductor, just like the ball ended up at the back of the wagon. And what we see is negative charges that build up at the back of the wagon, leaving positive charges behind at the front of the wagon. Not the wagon, the metal conductor. The second experiment took a piece of metal, a metal conductor, and it said, well, something is free to move around inside this conductor. It's either the positive charges or it's the negative charges. And we know that temperature tells us the average kinetic energy of the molecules in that material. If we heat up some material, the molecules will move faster. They'll vibrate more. And if they're free to move around, they'll move with more speed. If we keep heating it up, they'll move faster and faster. And pretty soon we can get it so hot that the atoms and molecules, whatever's free to move around in there, whatever those charge carriers are that are moving, who knows, are they the positives, are they the negatives, whatever's free to move around in there is moving so fast that they have enough energy they can break free from the surface and leave the solid material. That's what boiling is. When we have a pot of water and you put a flame underneath and add energy, the molecules start moving faster and faster and faster. And pretty soon, some of those molecules have so much kinetic energy, they can break free from the bonds that are holding it to the surface and become a gas. They can leave the surface and become a gas. That's boiling. And that's what we're doing with our metal. We're taking our metal, we're heating it up. Something in there is free to move around. It's moving faster and faster and faster as we get it hotter and hotter and hotter. And pretty soon it's moving so fast, those charge carriers are moving so fast, they can break free from the surface and leave the surface. They can boil off the surface of the metal. And when we do that, we see electrons leaving the surface of the metal. So 2 experiments that were done that lead us to believe that it's the electrons that are moving in our typical metal conductors. How do the electrons move through a typical metal wire? Well, first we have to fill the space in that metal conductor with an electric field. I'll have my electric field point to the left. Our electron sees this electric field and feels a force because it's a charged particle sitting in an electric field, and it starts to move to the right. And then it collides with an atom or molecule that makes up this conductive material. Maybe this is a copper wire that we're using to carry current in the wall in our house. Maybe it's something else. But the copper wire is made up of copper atoms and probably some impurities, and the electron moves and it might collide with one of those copper atoms and bounce back a little bit, and then it would have to reestablish itself and feel the effects of that electric field and start moving again in this direction. And then it collides with something and bounces back, and then it moves this way. And then it collides with something, and maybe it bounces back, and then it moves this way. And it keeps bouncing back and forth like this, but the overall movement is to the right, because that's the direction the electric field is pushing it. So the overall or average motion of our electrons is opposite the electric field because the electrons are negatively charged, and they move at some average speed that we call the drift velocity of the electrons. So they're moving, and then they bounce back a little bit, and then they move, and then they bounce back a little bit, and then they move some more, and they bounce back a little bit. But overall, they are moving to the right at some slower overall speed. When we factor in all these collisions and backward motion and everything, they have some overall net velocity to the right, and we call that the drift speed or the drift velocity of the electrons. And it's pretty slow. In our normal circuits, in our walls, you flip the switch for the light, and it would take an electron about an hour and a half to move 1 meter through the wire. So how is it that your lights come on right away? Well, the wire is full of electrons, kind of like having a garden hose that was full of water. And when you turn the faucet on, a little bit of water comes in one side, and what happens at the other end? Immediately, a little bit of water comes out the other end because the whole hose is full of water, and all the water starts moving. We don't have to wait for the water that just came out of the faucet to go all the way through the hose and come out the other end. As soon as it comes into the hose, it pushes something out the other end. Well, that's what happens here. As soon as you flip the switch, an electric field travels very quickly through the metal, filling it with an electric field. All the electrons in that wire, and that wire is full of electrons the whole way, feel the effect of that electric field, and they all start moving at the same time. So even though the electron at the light switch, it takes it an hour and a half to move 1 meter up the wall towards the light, there are electrons all through the wire that are moving through the light the whole time, causing your light to come on. Now, what's the other effect here? Our electron feels the effects of this electric field, starts moving to the right, and hits something and bounces back. And then it says, oh, wait, I want to get moving to the right again. It gets moving to the right, and as soon as it starts to get moving any amount, it hits something else and gets kind of stopped. Well, what's that doing? That's wasting a lot of energy, right? Our electron gains some kinetic energy and hits a molecule that makes up the wire. And now that molecule that makes up the wire starts to vibrate a little bit faster. Well, what does that tell us about the wire? The wire is now hotter, right? Because temperature tells us the average kinetic energy of the molecules that make up the substance. So as that electron feels the force from the electric field and starts to move, it collides with the atoms and molecules that make up the wire. They pick up some energy and start to vibrate more, which means our wire is hotter. So we're losing some energy from the current, from the movement of the electrons in the circuit to heating up the wire. That is resistance. Up until now, we were a little loose with our terms. We said we either have something that's an electrical insulator or an electrical conductor. But it's not quite that easy. There are different levels, there are different degrees of electrical conductors. So something might be a really super good conductor, and then something else might be a conductor, but not quite as good. Copper conducts very well. Aluminum is also a decent conductor of electricity, but not quite as good as copper. And so we have a lot of materials that have slightly different degrees of conductivity, and we can measure that, and you can look materials up in tables and books and figure out what the conductivity is. How good a conductor is it? Or inversely, we can figure out the resistivity of that material. So we'll talk about those terms in a minute. Let's think about this situation for a second. We have some type of conductor in the shape of a wire, and we want electric charges to move through this wire. What do you think would impact the flow of electric charges through this wire? There should be a few things that pop into your mind right away. One, we just talked about the type of material this is. Some materials, the electrons can move through them a little freer than other materials. Other materials, they collide, the electrons collide a little bit more, and so they have more resistance. So the resistance of this wire, one of the things it depends on is the material that the wire is made out of, how well it conducts electricity. We call that rho the resistivity of the material. The resistance trying to get through this wire is determined, one, by the material that wire is made out of. What else would the resistance depend on? This is how difficult is it for the electron to get from one end of my wire to the other end of my wire. It would also depend on the length of the wire. The longer that wire is, the harder it is for the electron to get to the other side. So the length of the wire should be in my equation. And what else might it depend on? Maybe think about flowing water through a pipe. What would make it easier or more difficult to flow a given amount of water through a pipe? The diameter of the pipe, right? You get a bigger diameter pipe, it's easier to flow water through it. If you get a smaller diameter pipe, it's a little harder to get the water to flow through it. So the same is true here. So the resistance is a combination of the material and its shape and size, how it's made. The resistivity is just a function of the material. So if I have a given amount of copper, copper has a certain resistivity. That's something we can look up. But if I wanted to know the resistance of a copper wire, I would have to know more than just that it's made out of copper. I would have to know what its cross-sectional area is and what its length is. And sometimes we talk about conductivity. Conductivity and resistivity are just inverses of each other. So if something has a big conductivity, it's a good conductor, it would have a very low resistivity, and vice versa. Let's think about what happens in our typical metal conductors when we run a current through them. We already talked about the fact that just the act of running a current through a conductive material will cause that material to heat up a little bit because the material has some resistance, which means the electrons, as they try to move through the material, will collide and give energy to the atoms and molecules that make up the material. And what is that energy? It's in the form of heat. The conductive material heats up a little bit. But what happens if we heat up the material? As you add energy to the material, let's say we're trying to flow a current through a material, and then we want to heat that material up and see what happens to the resistivity of the material, see what happens to the current we're trying to flow through it. So I have a wire here carrying some current, and I take out my match and light it and hold it over the wire. Well, I'm adding a lot of energy to the atoms and molecules that make up the wire. They're getting hotter. What does that mean? It means they have more kinetic energy now. They are vibrating more. And if they are vibrating more, what happens to the electrons as it tries to get through? Well, there's more of a chance for them colliding with the atoms and molecules. If the atoms and molecules are kind of not moving very much, the electron can get through a little easier. If the atoms and molecules are wiggling more, it's a little harder for the electrons to get through. So the resistivity increases. The resistivity of my metal conductor increases as I raise its temperature. What we end up with is a graph that looks something like this. The resistivity, as the temperature increases, also increases. This is for our typical metal conductors. Semiconductors have a very different mechanism, and their conductivity actually increases with temperature because more electrons are being excited into the conduction band. But we'll focus on typical metal conductors for the purposes of this class. And there are some special materials that as we bring the temperature down, the resistivity comes down and down and down until it actually goes to zero. Not low, not close to zero, it actually goes to zero resistance. And they've taken materials like this and set up current and taken out the source of potential difference, taken out the battery. And what would happen in a normal circuit? It's like taking a box and trying to push it across the floor. You give it a push, and very quickly, what happens to that box? It slows down and comes to a stop because of friction between the box and the floor. Well, resistivity is like electrical friction. And you give all those electrons a push with a battery, hook up a battery, the battery fills the conductive material with an electric field, and all the electrons start to move. And if you take away the electric field, if you take away the battery, then those electrons, because there's some resistance, very quickly slow down and come to rest. But if there's no resistance, those electrons will keep going forever because they have inertia. They want to keep going in a straight line forever. And that's what they've seen. They've set up current in superconducting rings, removed the source of potential difference, and the current just persists. Zero resistance. And this is huge because we lose a lot of energy to electrical resistance in all of our devices and transmitting energy and all these things. The problem is this temperature where this occurs, we call that the critical temperature, TC. The critical temperature is very low, and for a long time it was very low. They had to use liquid helium, which was super expensive, to cool down the materials to become superconducting. Nowadays, they've developed what we call high temperature superconductors. They work at liquid nitrogen temperatures. So we're still talking about -200 degrees Celsius, but at least we can use liquid nitrogen to get the wire cool enough, which is much less expensive and much more abundant than liquid helium.